Hello everyone. Today we are going to talk about the geometry of play, inclusive sensory design. My name is Muhammad Mukridi Muhammad Asabdi with my two other friends.
My name is Muhammad Afiq Amami Jaafar.
And my name is Audat Seri binti Asmadi.
Today we are going to talk about this topic carefully and detailed. So stay with us. Okay, for today I am going to introduce to you about this topic. Okay. The Sensory and Mathematical Discovery Garden at Greenview Primary School aims to make mathematics more engaging by allowing students to explore mathematical ideas through real-life interaction. By interaction, which means the physical interaction that students will have with our design. The second one is the main structure is a tetrahedral climbing frame chosen because it is a simple and stable three-dimensional shape made of triangles. As we all know, triangle is one of the most stable shapes that we got out there. Okay, the structure helps students understand key geometric concepts such as coordinates, planes, and spatial relationships through hands-on learning. By exploring this tetrahedral playground structure, students will be able to understand the spatial concept behind this. And research by Yusuf and Ismail 2020 shows that using 3D models and physical movement can improve students' understanding on three-dimensional shapes. The project also emphasizes safety and accessibility, ensuring the structure function as both a playground feature and a learning tool. So students hopefully will be learning geometrical and spatial concept from this playground structure.
So we move to the design idea, safety and inclusivity. Okay, to design a tetrahedral that is suitable for all students, including for students that limited mobility, we design a structure tetrahedral design, which has a three ground point and one central peak, and generate in a 3D Cartesian system. Okay, this is the four coordinates, which is A for this 000, B 400, C 2 3.5 and 0, and the P is 2 1.2 and 2.5. For dimensional justifications, the tetrahedral has a wide base, which is if you look at this, we can know that every side of the base have a side of approximately 4 meters each. Okay, the wide base support area keeping the center of the gravity within the parameter for maximum stability. Okay, for optimal height, which is the peak have a height of 2.5 meter, which is it is enough for balance physical challenge and safe for daily school use, which is 2.5 meter is not too high or too low. It's just suitable for both physical challenge and still safe for the students. Okay, the last is inclusivity focus. Our tactical mural panel are easily accessible for students with limited mobility, promoting the tactical exploration.
So moving on to the vector analysis, as both a teacher and designer, it's important for us to demonstrate that the structure is stable using mathematical analysis rather than relying on simple tools such as protractors or other measuring tools. Okay, therefore, vector theory is applied to analyze the structural and stability and geometric properties of the design. Okay, so now we are going to calculate the surface area of the tetrahedron. Okay, so to determine the strength and stability of the base, it is important for us to calculate its area. First, we define two vectors that start from point A, which is AB and AC. To get AB, we subtract between B and A, and AC between C and A. Okay, so AB will get 400, and AC will get 2, 3.5, and 0. So now we are going to calculate the AB and AC. So we using the concept of cross product. So now we are going to calculate the determinant. Okay, so for I, so 0 times 0 minus 3.5 times 0, and we will get 0. For J, we will start with 0 times 2 minus 4 times 0. And we will get 0. Okay, so now for k, to get k, we multiply 4 and 3.5 and minus the product of 0 times 2, and we will get 14. So the resulting vector is 0, 0, 14, and the magnitude is 14. So the area of the triangular base ABC is half the magnitude of the cross product of these two vectors. By two vectors, we are referring to AB and AC. Okay, so the area of base is half of the magnitude of the cross product. So by times with half, and we get 7 meters square. Okay, so the calculation shows that the base provides 7 meters square of ground contact area with the surface. This large contact area improves the stability of the structure by distributing the weight of the structure and the students more evenly. So as we all know, the larger the surface area, the more stable it becomes. As a result, the risk of tilting or imbalance during use is reduced.
Okay, so now we move to the stability and symmetry analysis. Okay, symmetry mandate. To maximize the structural equilibrium, the P must be vertically aligned with the triangular base geometric center. Okay, so we assume the base center as a Q. So the first we need to calculate the coordinate of the base center, the centroid, which is Q. Okay, to calculate it is just simple. We just need to the sum of the three bases, which is 4 coordinate x. We just need to plus, which is x coordinate for A, x coordinate for B, and x coordinate for C. And for Y, it is repeatable just as for x coordinates. So if after we substitute with those coordinates, we will get the central coordinate, which is 2, 1.17, and 0. Okay, for the stability and symmetry analysis, to confirm the P is centered vertically, we examine the relationship between the horizontal base vector AQ and the vector QP. If the PP is centered vertically, which ground centroid, the resulting vector between AG and GP must be 90 degrees. So we need to calculate the angle between AG and GP. Okay, first we need to find the vector of AG, which is we just reduce the coordinate of G minus coordinate of A, and we got 2, 1.17 and 0. For vector GB, we just minus P and G. So we will get 0, 0.03, and 2.5. For calculating the product AG times GB, we just multiply both vector, which is vector AG and vector GP. So we just times for x. For x, we just times 2 times 0, 1.17 times 0.07, and 0 times 2.5. And we will get the answer, which is 0.0351. Okay, for find the magnitude of AG, we just need to square root the square of those three vectors, which is 2 square, 1.17 square, and 0 square, which is 2.32. And for AG, we just do the same, and we will got 2.5. To find the angle between AG and GB, we use the dot product formula, which is r cos theta equal to AG times GP divided by the dot product 0.351, and we got the theta, which is 89.65 degree. Okay, for the stability conclusion, the angle of 89.65 is nearly identical to the ideal 90 degree, confirming the structure is perfectly upright. Okay, for the last is structural benefits. Perfectly aligned. The P is actually centered for the balance loads, prevent pressure on only one side of the frame. Okay, and the last, safety and durability, guaranteed to be stable and long lasting for student use.
So let's move to the mural planning and spatial visibility. So in this structure, there are two planes, or we call it surfaces. So the first plane is plane ABC, which is A, B, and C, which is their ground plane, or we call it as base. So the second one is PAB. PAB is PAB, so where the mural wall is located. So the goal is to find the angle between the mural wall and the ground. So if the wall perfectly 90 degree, which is vertical, and less than 90 degree, which is wall is tighter, hence we calculate the tilt of the mirror. A normal vector are used. Why we use normal vector here? This is because vector is perpendicular to the surface. So to find the angle between two planes, we actually calculate the angle between their normal vectors. So, for the first step, we need to find the normal vector of the ground ABC. Since the base flat on the xy plane, its normal vector points straight up along the z-axis. So, z-axis is the vertical one. So, we need to find n1. N1 is 001, which is located here. Normal vector for the mural PAB is from the cross product AB times AP. So we got 0, -10, and 4.8. So the orientation of the mural wall is this one. So this is the dot product formula that we are going to use. For the first step is step A, because we need to use dot product. So this is the value that we get the previous slide. So we use for dot product n1 dot n2. So 0 times 0 plus 0 times -10 plus 1 times 4.8. So we evaluate this and we get 4.8. So next step is magnitude of the vector. So after we get the n1, so n1 is 0.01, and then 0 square, 0 square, and 1 square. So we need to plus it and square it. So we get 1. So for the next one is n2, which is 0, -10, and 4.8. So we need to square like this. And we get 11.09. And the step C is the final step. Evaluate the angle. So we substitute all the value that we get. So 4.8 is dot product, and this is magnitude. This is magnitude. So we get 64.35 degree. So this is the final mural planning that we discussed together. So this is the visual representation of the sensory structure. So here we have PAB, which is we calculate already to put mural wall, and then it's very beautiful, right?
Right. Yes. Yes.
There is one student looking at the mural with head straight up. So he didn't need to look at the mural effortlessly. So the next student is climbing using the rope climbing. To ensure the student is safer, so there is one teacher observe two students. So on the justification, the mural forms an angle of 64.35 degree with the ground. This means the wall is tightened, not fully vertical. So why this angle is good for student? First is to improve visibility for primary school student. Visibility for what? To see the mural. For the second one is avoid make students tilt their head too much. As you can see at the previous slide, the student is not tilt their head too much. Just You get that? For the third one is make the world closer to the material eye level of children. Okay, for the last one is reflection on the design process. So being involved in this design process changed my perspective on 3D geometry. So previously, I saw vectors only as abstract formulas used in examination. So however, applying them in a real life and inclusive structure helped me realize that geometry is more than that. So it ensures safety, balance, and fairness while helping solve real world problems that benefits society.
So, for the growth of understanding, there are few things that we can get from completing this task. First, it changed our perspective on 3D geometry and vectors. Second, we found that mathematics is not only formulas but real-world application. Third, vectors provide clearer structural analysis than simple angle measurement. And fourth, vector cross product determines surface direction and stability. And the last one, it helps predict real situation such as sunlight direction on mural and pressure when children climb on the wall. Okay, so influence on my teaching. How does this task influence my teaching from here onwards? First, mathematics should be connected to real life situations. Second, it helps students understand 3D shapes and structural stability concepts better. And third, it encourages deeper mathematical thinking. And fourth, it supports inclusive learning environments. And fifth, it aligns with Universal Design for Learning, UDL. And the last one, we can conclude that mathematics help create a safe and accessible space for all students. In conclusion, we can identify mathematics in real-world design. 3D geometry and vector calculus improve design accuracy. Second, coordinate surface area and direction ensures safe structure. Third, mathematics transform abstract theory into real applications.
And the fourth one is support better thinking skills through geometric modeling. And fifth,
And the fifth is to design thinking approach creates inclusive learning space.
That's all from us. Thank you for your attention.
Bye.
Bye.